All right, so we've got a cold air standard Otto cycle, and I'm given a lot of the same information as the previous problem. Really the only difference is that I'm assuming that specific heats are relatively constant, or are constant, and they're taken at 25 degrees Celsius, or about 300 Kelvin. So CV, CP, and K, which is the ratio of CP and CV, those are given over there in my assumptions. Those are all taken at 300 Kelvin for air, and now I'm ready to go through and figure out my solution. So my thermal efficiency equation in the previous problem, I already put this together. The only step further that I can take is, because I'm assuming that specific heats are constant, any delta U's can be approximated as CV delta T's. So I've just made my life a little bit easier, and I shouldn't have to pick up my ideal air tables at all. If you're making the cold air standard assumptions, then you shouldn't have to touch those ideal air tables at all, and it'll make your life a little bit easier. No interpolation. All right, so I'm not going to do a governing equation for all those pressures. I'll kind of work my way around the cycle and calculate them as I go through the cycle. So for state 1, well, I need to know the temperature, and lucky me, I know it, and I also know the pressure. Now I'm ready to go to state 2. Well, just like the previous problem, from state 1 to state 2, I've got an isentropic compression process for an ideal gas, so I can apply my isentropic relationship for an ideal gas, and in this case, I can use the one that makes the assumption that specific heats are constant. So remember, you've got 5 isentropic relationships that you can use. 2 of them if you do not make the assumption of specific heats being constant, and 3 of them if you do. All right, so here's my isentropic relationship. I know V1 over V2, that's just R, and as long as my temperatures are in absolute temperature units, I can calculate what my T2 is. And you'll notice I haven't rounded off here. I won't round off until the very end once I plug everything into that thermal efficiency equation. Now it's time for me to figure out what my pressure at state 2 is. I've got 2 choices. I can use my ideal gas law, which is always valid, no matter what kind of process I have, because I'm assuming that the air behaves as an ideal gas, or I can use an isentropic relationship applied between state 1 and state 2, since I have an isentropic process for an ideal gas. And I'm going to choose the second one. Like I said, I could use the ideal gas law, and we're going to do that for state 3 in just a second, so you see how that's applied. And I would encourage you to solve it both ways, just to prove to yourself that both of them will give you the same answer. But in this case, I'm going to go ahead and just do the isentropic compression or isentropic relationship. And if I plug in the numbers, I get my P2 value. All right, so now it's time for state 3. So I don't have an isentropic process, so I can't use one of those isentropic relationships, but I can use my first law. So I've got Qn equals U2 or U3 minus U2, and because I'm making the assumption that specific heats are constant, any delta U's can be approximated as CV delta T's, and I can directly solve for T3. Now I'm ready to solve for my pressure, and for that I'm going to use my ideal gas law. So because I'm assuming that air behaves as an ideal gas, that quantity, PV over RT, is equal to 1. And it's equal to 1 at state 2, at state 3, at state 1, at state 4. So because each of these things on either side of the equal sign are equal to 1, they're equal to each other. All right, and this is really convenient because that specific gas constant goes away. Those are, on either side of the equal sign. The specific volumes go away because V2 and V3 are equal to one another. State 2 to 3, that's a constant volume process. And so I can just easily calculate what P3 is from the following formula. Now I'm ready for state 4. So now from 3 to 4, I do have an isentropic process, and so I can use an isentropic relationship, and I do know that V3 over V2 is equal to V2 over V1, just because looking at those constant volume processes, and if I plug everything in, I can calculate what my T4 is. And the same thing, I can use an isentropic relationship to figure out what P4 is, and if I plug everything in, I get my P4. Okay. And so once again, if I take all those temperatures, I didn't round off, I just plugged it right into the equation, I ended up getting 60.2%. So, all right, well, hope that was helpful. Thank you for watching.